every transaction, economically justified, rationally justified, is a transaction of getting more than you give. To you, right, personally speaking. Consumer surplus is the difference between the total utility and the costs. I give costs, I pay expenditure, right? It goes away from my pocket, right? Exactly. But utility is what I gain from it. And the difference between the two is the surplus I gain. Consumer, as a consumer. But because these two guys are obviously functions of Q, right? Cost is also a function of Q. What is a cost? What's the simplest expression for cost? Price times quantity purchased, right? However many you purchase, each item has a price, right? It might be flat price, it might be not flat, based on the quantity, right? But still, you can find the cost. You know the flat, you know it's not flat, whatever, you can find it, easy. That means that, obviously, consumer surplus is also a function of quantity, obviously, right? Must be. Okay, now, this is it. But that means that utility, if you isolate for utility, it's of course combination of two. Inside utility, for you, it's not just consumer surplus that you will experience, but it's also the costs that you will have to give. So a combination of these two, I'm just rearranging the equation. You see, I'm isolating the utility, pushing it on, obviously, right? For me, that's more reasonable. I think about utility as combination of consumer surplus and cost together. That's also very important for the understanding of the meaning behind the areas inside the triangular shape. The moment we change the marginal utility to price, then every level, vertical level, is a price. Then there is a way of talking about price being cutting the triangle into two halves, the upper and the lower, but I'm not going to talk about it right now. We have to get there, we have to do one more step. Okay, so we understand consumer surplus now. Now, we have to now try to visualize. We will come back to this picture. You remember, right, this triangle? We will see it again. He'll be in terms of price. That will be the demand curve, and that would be the last step where we'll be able to analyze the area under a certain level as being a expenditure below, and on top of that being the surplus. Just like the words say themselves, right? Surplus is extra, the bottom is the base, the expense base, right? Right, what you have to give. Exactly. The consumer surplus. The consumer surplus, I have the equation for consumer surplus. It is equal to utility subtracting what I get, subtracting what I give, cost. And in terms of, let me just write down P times Q, as if it's not flat fee, just a regular purchasing of items with the static fee, static price. Okay? Now, isn't that a function? It's a function. Okay, how would that function look like? And why would you even care about the way it looks like? Well, don't you want to maximize something? Don't you want to maximize your consumer surplus? Right? You want to realize as much of utility as you can, basically, right? Which means either less cost, right? Or you're manifesting your utility. You're gaining much of the utility that it has for you. The demand, right? Meeting your demand. Okay, now, but calculus, graphs, math, right? How would you see the maximum of consumer surplus? Wouldn't that be good if you could see consumer surplus as a graph of a parabola? And then just locate the maximum, the vertex, and that would give you the Q? That would be it, right? And now, let's actually not do it. Let's not do it because we don't know the price. We're talking in abstract, any price. So, we need to use calculus. We need to say, look, in order for me to maximize it, or in general, an idea of maximizing a certain process, visually speaking, implies reaching the vertex, reaching the peak. But every peak is at least the local max. Can be the absolute max, can be just the local max. In our cases, it's the absolute and the local at the same time. The local max, which it must be the vertex anyway, even if it was the minimum, right? It's more general. That must be a vertex. It can be maximum, can be minimum, can be local, can be absolute, right? But it must be the vertex. If I'm maximizing. Yes, and it's the maximum because I'm maximizing. If I was minimizing, it would be the vertex, but it would be the bottom. It will be based on the structure. And of course, because here we have UQ, obviously utility, and because it is with negative A value, it's the shape of the structure, even though this guy will still be same kind of a shape, right? This minus PQ wouldn't change too much. It would just move it a little bit, right? Maybe it will stretch it, maybe it will compress it, right? In terms of just math, right? It wouldn't really, it wouldn't make it upside down, right? You'll have to multiply the whole thing by negative something, right? To make it upside down. That's a completely different thing. Yeah, really nothing. So the same overall shape is going to be present. Which means, yes, you justify to yourself that I'm still talking about potentially localizing maximum only. There's no minimum here. It doesn't exist here. Okay, so obviously, and we're not talking about minimizing consumer surplus. We're talking about maximizing consumer surplus. Okay. But if it is then the top of this always going down curve, diminishing, right? Diminishing marginal utility. The assumption of diminishing marginal utility is the fact that the drive behind this curve is always diminishing, going down. That will be the second derivative. That will be the rate of change behind the slope, right? The acceleration is in physics, right? But here it will be the diminishing marginal utility. Okay. Well, how do we find the peak? Isn't that the place where the graph slope is momentarily zero, which means horizontal? I'm trying to find the zero. I'm equating to zero the first derivative of the utility, which is marginal utility. We're not talking about marginal utility right now. We're talking about consumer surplus. And we don't even know what the price is. Therefore, if we did know the price, yes, that would be something like that, right? Well, maybe there'll be something extra here, right? Yes, so obviously, if you're trying to look for the maximum, the slope must be 0, which means your derivative function must be 0. And secondly, this is what I'm interested in, this guy. I'm taking his derivative, consumer surplus, first derivative, and I'm using Newton's notation, just prime sign on top, instead of writing dy dx, whatever, dcs, dq, just one symbol, prime, here, that's it. Well, if I take, well, I have to take of both guys here, so I'm going to have to take derivative, the first derivative of the utility function, and I know what's his name. Marginal utility is the first derivative of the utility, right? And I have to take derivative of this guy, of the expenses, right? Now, with the p and the q, wait a second, isn't the p the scalar multiple in front of the variable? Because the variable is very q, right? So doesn't that mean that just the minus p will survive the differentiation, right? Right? So 1 power 1 will come down, right? And it will disappear, it will become 0, so it will be just minus p, right? Minus price, right? Minus price times 1. But it will be just minus price, right? Eventually. Okay, so that's the derivative of the structure of the consumer surplus. Okay, now, what is the state of consumer surplus that you are trying to achieve? You are trying to achieve the greatest state, the highest point. What happens at the highest point? Its slope equals to 0. Doesn't that mean that the first derivative of the consumer surplus equation should also be 0? Because that's the same thing? Yes. The derivative of the consumer surplus being 0 is exactly the point where its graph of the original consumer surplus becomes flat. Okay, so equating first derivative of any structure to 0 means looking for the maximum or the minimum. That's what it means. Eventually, all questions of optimization they end up at the place where you equate some derivative to 0. Okay, so now, what does that mean? How can this structure be equal to 0? The idea is this, that if you want to maximize your consumer surplus, you will eventually get to the situation where your utility derivative, which is marginal utility in other words, by the way, 3 lines is definition, right? Equal by definition. It's the same thing. Equals to p. That's the point, right? The whole gist behind the optimal purchase rule that you can follow to get the optimal purchase is this. Is to follow the amount of quantity that will give you first derivative of utility function equal to the price. Basically, marginal utility equal to the price. So, when marginal utility equals to price, you got your optimal purchasing option. And when obviously prices can change, right? When you change your prices, what happens? Don't you get different levels of marginal utility? We were talking about in the beginning, remember when I said that you can change the y-axis from marginal utility to price? That's when it happens. That's when you're trying to follow the optimal purchasing rule. That's when you're trying to maximize your utility. Maximize your consumer surplus, right? By gaining the most of the utility that you have for that certain item, certain product. So eventually, that graph is exactly the same graph, it gets replicated, but now it looks like it's the same thing, right? We start from 400 for our present, then we stop here at 100, Q, and now here, instead of marginal utility, we're saying, well, because we already figured out that equating these two things means being optimal, trying to get the optimal consumer surplus, the maximum consumer surplus, which means being optimal in your purchasing choices. Well, that's it, right? Price in terms of dollars, quantity in terms of whatever number. So you go, and then, depending on the price, right? Whatever the prices are, right? 300, 200, $100 or whatever, 0, right? What happens is that at any level of a price, you will have this triangle created, the top and the bottom, right? So if let's say 200, at the 200 level, there's the triangle on top. Let me call him triangle with the area, right? He has an area. Let me call it area 1. Okay. Then what else is there? What is the quantity that you have to choose in order to optimize your purchasing habit, or to make a most perfect optimized purchasing decision to increase, to maximize your consumer surplus in this situation? Your quantity, what if the price was 200 per item? You have to take whatever, right? That particular, we can find it by using the equation, right? So whatever that is, right? Let's say Q sub 200 price. Now, what is the shape below the triangular shape? Whatever, it's a square or a rectangle. Let me call it shape A2. And I'm talking about these two shapes. I'm not talking about that shape. That's outside, that's extra stuff, right? You don't have that shape. The bottom and the top shape, what are these? What do you think these are? The top triangle and the bottom rectangle. What do you think the areas of those shapes represent? This is what? This is the price difference between the price at which you're purchasing and the 0. That's the price you paid, right? 200. What happens? That's the vertical. That's the height of your square. What's the width of your square? Isn't that the quantity? What happens when you multiply quantity by price? Don't you get the cost? So that's the cost, right? What can it be? It's just the cost. So height times width, price times quantity is cost. So of course it's a cost. Can you not agree with that? That's just cost. Now what about the top? By the way, what was cost plus what? Equal to what? Remember that equation? Plus consumer surplus was the total utility. Total utility, right? Exactly. That's the thing that you have function for, right? Wait a second. So wouldn't adding two areas be very useful if this area represented the consumer surplus and the total area represents the utility total? The whole thing, right? The whole area at that level, right? Between the quantity and the whole thing, right? Basically. But not this part, right? Not the part of quantity that you did not purchase, obviously. You didn't manifest it, you didn't realize it. Yeah, that's potential, exactly, yes. So that area is consumer surplus. That's the extra. You see it on top. It's the extra thing you have. It's the consumer surplus. And the whole thing is utility total, because if you're going to take this marginal utility graph, which now we call price, because we're talking about consumer surplus being optimized. If you take that graph now as a function of marginal utility and say that, you know what, I remember that was the first derivative of the utility. So what if I take the integral? An integral looks like S because it represents sum of all tiny rectangles together, area of all tiny rectangles in your shape. If you calculate the areas of all tiny strips, if you cut it in as many strips as you can to make a proper approximation to the area, and if you add them all up, you will get the integral of the graph that you're dealing with. And because your graph is the marginal utility graph, and because it is the first derivative of the utility, and because you are doing integration, which is basically multiplication or addition of the rectangles, where the height is the very graph height, very y value, which is the price or marginal utility, or in other words, u prime q, and where the length is the q, we talk about dq, like differential q, tiny little difference of q. If you're going to collect all those tiny little q's multiplied by the heights, areas on top of each other, it's called the Riemann sum. You will end up getting a good enough approximation for the area of the thing that you're cutting. And the perfect approximation is the idea of the integration, of the integral, total, whole, altogether, sum. That's what it means, right? Integral, S is a big S, it's a sum. Sum of the products of these guys is sum of the areas of tiny strips. Well, what happens when you integrate a derivative of a function? That's called the Fundamental Theorem of Calculus. The whole beauty of calculus is that if you're going to integrate a derivative of something, you go backwards to the original. That's the thing. Integration, it brings you backwards. Integration, it basically cancels the previous action of differentiation. And differentiation will cancel the previous action of integration. They're inverses. One is cutting original into its, like this change structure, like understanding the original in terms of the change. And the other one is taking the change and understanding the thing that was changing. Go backwards in this process, right? Which, if you realize in this case, well, you're trying to recreate the original u, because you're integrating the derivative of the utility, which is called marginal utility, right? You call it marginal utility, but it was always the derivative of the utility by definition, and you're now integrating it across the q, so you're basically getting back the u, right? So the overall, so the whole total integral area of the whole shape, whenever you stop, whatever quantity you choose, according to your consumer optimal choice, well, the whole area will represent the whole utility. Well, if the whole area is the whole utility, then isn't that what I just said gets to hold more truth, even more truth, right? If the whole thing is utility, function, area represents the utility, and if the bottom part already represented cost, then the other part should just have no other choice but to represent consumer surplus.